Hello, this is Physics 1020 and 1090. This is a lecture for Monday, March 23rd. We're dealing with Chapter 25, Optical Instruments, but we've really finished the chapter. So here in video 3 of this lecture, we're going to be talking about what's on Exam 3. Exam 3 covers 4 chapters. Chapter 22 on the reflection and refraction of light. Chapter 23 about mirrors and lenses. Chapter 24 about wave optics. And Chapter 25 about optical instruments. We covered a lot of ground in these 4 chapters, and I've decided to narrow the topics down to just 12 topics. So we're going to focus on these 12 topics for Exam 3. Let's go through them one by one. Start in Chapter 22. We talked about the energy of a photon. So this concept of light being both a wave and a particle with energy. To understand or to really calculate the energy of a photon, you need Planck's constant h. So you'll need to have that value, and you need the relationship that the energy of a photon is equal to Planck's constant times the frequency of the light. You also want to remember the relationship from earlier in the semester that the wavelength lambda times the frequency f is equal to the speed of light. That way, if I give you a wavelength lambda, you can get the frequency and then get the energy of the photon. Oftentimes, the energy of a photon is very small when expressed in joules, so you need to be able to convert the energies to an electron volt, a very convenient use of energy for single atoms and photons. You want to have something to compare these energy values to, so you want to keep in mind that thermal energies, that is, energies that atoms have when they're bouncing around at room temperature, is roughly around 1/40th of an electron volt. And that bonds holding atoms in a molecule together typically have energies of 10 to 100 electron volts. So if you come up with a photon energy of, say, 1/100th of an electron volt, you know that it's not going to be breaking bonds. Finally, you want to have some idea of the electromagnetic spectrum. We talked about that earlier in the semester, but remember we talked about radio waves, microwaves, infrared radiation, the visible spectrum, ultraviolet, X-rays, gamma rays. However, we added this idea lately in Chapter 22 about the energy of the photon. So you want to go back and revisit that information about electromagnetic spectrum, including ideas about the energy of a photon. Second concept we have is the law of reflection. And the law of reflection is very easy. The incident angle is the reflected angle. Remember, you measure these angles from a perpendicular line relative to, say, a mirror. And the type of equations we often find, or questions we often find, that I call a corner cube type problem, where you have 2 mirrors separated by an angle theta. Light comes in at an angle phi with respect to that mirror. It bounces off here, and you're trying to find the zeta angle of the ray that comes off. And for a true corner cube where theta was 90, that would be just the same as the incident angle. But for corner cubes, it's really, the law of reflection is very easy. It's just a little bit of geometry in order to solve the problem. Number 3 is refraction, still in Chapter 22. You need to know what the index of refraction is. N is usually given as the index of refraction for different materials. For air, it's typically 1. And you need to be able to understand Snell's law. Snell's law says that suppose you have light coming in an index N1 and makes the angle theta1 with the perpendicular. It goes into material 2 and it bends the angle theta2, and that has the index of refraction N2. Snell's law says N1 sine theta 1 equals N2 sine theta 2. Now, one result from Snell's law is the idea of total internal reflection. If the refracted ray, when going from a large index to a small index, actually is greater than 90 degrees, then you're going to have total internal reflection where all the light just bounces and reflects off the surface. You can find the critical angle at which you just get total internal reflection by taking sine of the critical angle as 1 over n, where I'm assuming the outside is in air, so that's the index of refraction of air. So then you'd have to find the critical angle. You'd take the critical angle as inverse sine of 1 over n. So make sure you know how to do inverse trigonometric functions to find the critical angle. Next up was some material that wasn't really in the book, so you have to get it from your notes. We talked about color vision and how your eye has 3 types of cones that are sensitive to red, green, and blue light. So white light is when all the cones are activated, so red light plus green light plus blue light is going to correspond to white light. Now if you mix red and green light, your brain sees it as yellow. So if you took red and green light spotlights and you merged them together, you'd see yellow light. And if you took a laser that was just a single wavelength in the yellow part of the spectrum, you'd see that as yellow light. So you can get yellow light either by mixing colors or by having a pure color that's between red and green. Another mixture, green plus blue, is sort of a blue-green called cyan. And red plus blue is sort of almost a reddish violet color called magenta. Magenta is interesting in that there's no single wavelength that can activate the red and the blue receptors without activating the green. So magenta can only be produced by color mixing. Then we went on to chapter 23 and talked about mirrors. Okay, so the mirrors, you can have a concave mirror like this one, where you have an object in front of the mirror. This is the mirror's focal point. And you can draw 3 rays. And we talked about these rays. A ray straight across comes out through the focal point. A ray through the focal point comes out straight across. And a ray that comes into the center comes out symmetrically. And they all meet right here, and that becomes your image. So you can find an image produced by a given object. And the mirror equation is 1 over the focal length is equal to 1 over the object distance plus 1 over the image distance. And the object distance would be the distance from the object to the mirror, and the image distance is from the image to the mirror. And the magnification is minus image distance over object distance. You want to know what the difference is between a real and virtual image. In this case, the light rays actually come and meet here. You could put a piece of film there and develop that image. That's a real image. You have, in this case, the image is upside down compared to the object. It's an inverted image. And in this case, it's not entirely obvious, but it looks like the image is a little bit bigger than the object, so it's a magnified image. If you had your object inside the focal length, you'd see a very different situation. You'd be getting a virtual upright image. You can also have a convex lens where the lens is bent the opposite direction. The mirror is bent the opposite direction. And it has a focal length. And you have your object here, and its 3 rays are slightly different, as we discussed in class. But this case here forms a small image right here, which is going to be a virtual image because the light doesn't actually converge there. It just appears to converge from there when we extrapolate back. It's upright because it's facing upward, and it's minified because it's a much smaller image. So you want to be comfortable with mirrors, both concave and convex. Halfway through, number 7, lenses, thin lenses. Thin lenses, you have 2 types. Converging lens. A converging lens has an object in front of the lens, focal points, and 3 rays again, comes in horizontal, goes through the focal point, and comes out horizontal, goes through the center of the lens, in which case it's undeflected. And in this case, they all meet right here at the image. That's a real image, inverted and minified. Your thin lens equation is the same as your mirror equation. 1 over the focal length is equal to 1 over object distance plus 1 over image distance. Magnification is also the same. You can also have diverging lenses where the focal length is negative. The lines are a little bit different. In this case, they all converge to a virtual image that's upright and minified. For the converging lens, things look very different when the object is outside the focal point and inside the focal point. When you put an object inside the focal point, you get something that looks like a reading glasses or eyeglasses. On to chapter 24, wave optics. And the first thing, we spent a whole class talking about Young's double slit experiment. You take light of a certain wavelength and you shine it on a screen that has two small slits separated by a distance d. The light comes out of these slits, and on another screen, a distance L away, you get this series of interference fringes, light and dark spots. You can measure distance y from the central white spot to some other spot. And what's important in this case is whether it's constructive or destructive interference. And that depends on the extra distance this ray makes from this slit versus this slit. If the extra distance is 0, 1, 2, or 3 or so on wavelengths, you get constructive interference. You have m, the order of the fringe, times the wavelength is equal to the slit width times the distance on the screen divided by the distance between the screens, L. Okay, now if I asked you what was the distance between adjacent fringes, that would just be the distance between two adjacent integers, so really m would become 1, and you just get lambda as dy over L. You can figure out the wavelength of light from this equation. This was important historically because it was the first real demonstration of the wave nature of light. Another classic example of wave interference is thin films. So we're going to have a case here where we have a thin film. We want to make a non-reflective layer. So you have light coming in air. You have a piece of glass with index of refraction 1.5 and some kind of film or material layered on top of the glass. So now you have one reflective ray here and another reflective ray that goes all the way down and out. And these two reflected rays can interfere, and if you want a non-reflecting surface, you want destructive interference. So you want the extra distance this ray travels, which is 2d, you want that to be equal to half a wavelength in order to get destructive interference. And by half a wavelength, we mean the wavelength within the film, which is lambda over n. So you end up getting 2d is equal to lambda over 2n, or d is equal to lambda over 4n, is the condition for non-reflective surface. You can actually have any integer multiple of lambda. You can have 2 or 3 or 4 lambda. It would still work, but the thinnest possible layer would correspond to just lambda. Now, we can also get reflections and interference off of bubbles where you have air, water, air. And this brings in this important point that's always one of the more difficult issues for students. When you go from air to water, low index to high index, you get a 180-degree phase shift upon the reflection. We actually got 180 degrees phase shifts over here, but it happened on both of our reflections, so there was no relative phase shift between the two rays introduced, so we could ignore them. But now over here, you get a phase shift on this surface, but on the lower surface, you go from high to low index, no phase shift. So there's a 180-degree phase shift introduced just from the reflections. So if you wanted to have constructive interference, you would have to have a 180-degree phase shift, which basically shifts you by half a wavelength, and you'd have this extra distance would equal half a wavelength. So the extra distance, half a wavelength, is equal to lambda over 2. You'd end up getting the same equation here, but now it's constructive interference instead of destructive, and it's constructive because of these phase shifts that happen upon reflection. So you want to understand that difference and what happens when you introduce these phase shifts. The last topic in chapter 24 was polarization. A key idea in polarization is Malice's law. You have the intensity of light coming out of a polarizer is equal to the intensity going in times cosine squared theta, where theta is the angle between the polarization axis of the polarizer and the other light. So let's consider the case where you have unpolarized light initially, and then it goes through a polarizer. Okay, whenever you have unpolarized light goes through a polarizer, you immediately lose half of it. And now it's polarized light, in this case, horizontal. Now it goes through a second polarizer, sometimes called the analyzer, at an angle theta with respect to the first. Then you're going to have the light coming in is I naught over 2. The light going out is Malice's law. I naught over 2 times cosine squared theta. If theta is 90 degrees, you have cross polarizers, and cosine of 90 is 0, so you have no light coming out. One of the interesting things that always amazes me is you can have two crossed polarizers, and then you can put a third polarizer between them, and all of a sudden now you're getting light coming through all the way out the side, because the polarization rotates the polarization state of the light. So you want to be able to handle systems not just with, say, 2 polarizers, but 3, initially unpolarized, polarized, and then you have some intermediate case, and then cross polarizers are an example of type of problem you might be faced with. Polarization. On to chapter 25. In chapter 25, we really use chapter 25 to talk about 2 lens systems, telescopes and microscopes primarily. And here I show a picture of a compound microscope, have 2 lenses, an objective and an eyepiece that are separated by some known distance. Now, the way you solve a 2-lens system is first you have an object and you find the image that the objective produces, assuming the eyepiece wasn't even around. So you have object 1 here produces image 1 down here, real image. Then you say, okay, now I'm going to have this be my second object. Pretend the objective doesn't even exist. This is my object. Where's the image? Well, that object's inside the focal point of the eyepiece, so your image is now this big image down here. And you see it's a compound microscope. We're getting lots of magnification. So that's the case you have. That's the way you do it. Notice that you need to know that separation between the 2 lenses, because if you know the image 1 distance, then to find the object 2 distance, you take the separation between the lenses minus the image distance gives you the object distance. So that's the general way you solve 2-lens systems. We saw it for the compound microscope. We also saw it for the refracting telescope. Finally, number 12 is the eye. We spent a lecture talking about the eye. Remember, the eye has a lens and a retina which detects the light. You can have people who have problems with their vision. They're, say, farsighted or hyperopia. That means they can see distant objects, but they can't see nearby objects. They have some point called their near point, inside which they can't see. And you can figure out what sort of glasses you need in order to give a person who has farsighted or hyperopia and correct their vision. You can take some object that you want them to be able to see, and you can place it at their near point so they can see it, the image of that object at the near point. And you can actually prescribe what sort of glasses are needed in that case. Same thing with a myopic or a nearsighted person. They have a far point. They can't see anything beyond, or can't focus on anything beyond that point. So you can give them glasses so that they can focus on something from an object at infinity or a long ways away will cast its image at the far point, and they can see it, and you can figure out what lens you need to prescribe for that person. Oftentimes when we're talking about the eye in vision, we don't discuss the focal point length of the lens. We discuss its power, which is just 1 over the focal length. And therefore, the units of power are diopters, which is 1 over meter. So a very common question might be to ask you to prescribe a lens that will correct the vision for distance vision for a person with myopia who has a near point or a far point of 15 meters, and give me the answer in diopters. Those are 12 issues. Now, we covered a lot of other things, and I love them. They're all important, but I had to narrow down what was going to be on your exam. There's just too much. So here's the things that are not on the exam. I'm just going to run through them real quick. Dispersion, rainbows, Fresnel lens, spherical and chromatic aberration, coherence, single slit diffraction, Rayleigh criterion, diffraction gratings, Poisson spot, X-ray diffraction, interferometers, and LIGO. Optical coherence tomography, polarization by reflection, polarization by scattering, Brewster's angle, birefringence, visual acuity, and reflecting telescopes and Galilean telescopes. That Galilean telescope was particularly tricky because it had a negative object distance and a diverging lens in it. We'll two lens systems are game, but not Galilean telescope. So those are all wonderful topics. We talked about them. I hope you got something from them. But I'm trying to focus down this exam. We have enough going on. I wanted to get it down to just 12 topics. So I've described you the 12 topics. These things are things I hope you take away and you understand, but won't be on the exam 3. A few other notes about exam 3. It's going to be 6 questions, just like those practice exams I sent. 6 questions, and they're all multiple choice. That's good news and bad news. Multiple choice, easier. I mean, you can guess your solution. The problem is that with multiple choice, it's all or nothing. And there's only 6 questions. So if you make some dumb error and just click the wrong button or something, you lose 1/6. You go from 100% down to an 83. So you want to be careful when you are doing your exam to make sure that you don't make a dumb mistake, because it can cost you dearly on multiple choice. This is going to be a timed exam, so you're only going to have 70 minutes to do the exam. So you want to be keeping track of time and making sure that you don't get all the exam done and you're checking it over and over and then you time out and you end up with a 0. So you want to make sure that you keep track of time. I'm going to give you another practice exam, a third practice exam, which is going to be timed, so you'll have the experience of doing the timed exam on WebAssign. This is an open book exam. Open book, open notes. You can make a page of notes or not. It depends on you. You're certainly allowed to. You can really use anything. You could use the internet if you wanted to. What you can't use is you can't use another person. You have to do this exam by yourself. And we're sort of on honor system for that, but I'm going to be relying on your honesty. Every person does their own exam without getting any help. Don't go discuss the exam immediately with your friend, because you're going to have various times you can begin this exam within that Friday. So you can discuss the exam with your friends starting Saturday morning. So this is the plans for exam 3. Now, next class on Wednesday, we will spend the class solving those practice exams that I gave you and going over these 12 topics to make sure you're ready to go. All right, very good.